Hey guys, Miss Peterson here, and today we are talking about voltaic cells at non-standard condition. So these are voltaic cells not at 25 degrees Celsius and 1 atmosphere or 1 molar solutions, okay? Because guess what? Sometimes we don't do things the standard way. Sometimes we have to mix it up for different reasons. This is video 3 in our series on electrochemistry using the NMSI guided student guides. So let's talk about voltaic cells at non-standard conditions. Okay, so remember standard is 273 K, 25 degrees Celsius. Q is 1 because you got 1 molar for your products, 1 molar for your reactants, and that's where we get the E naught. Okay, but we can only use a lot of the things we've been doing if it's at standard conditions. When things change, we have to adjust. We can't use those standard values anymore. And there is an equation that we can use to take into account this adjustment. Okay, it's called the Nernst Equation. And it is the energy of that cell equals your standard energy. So this is your standard potential, the one that you get using those standard reduction potential charts. We have R, our gas constant, our energy one, the one with joules. F is our Faraday constant. It's on your equation sheet. N, remember, is the number of electrons exchanged in the balanced reaction. You can't forget to balance it. T, temperature in kelvins. And natural log of Q, where Q is our reaction quotient, products over reactants to the coefficient. You guys might remember these from equilibrium. Okay, so on the actual AP Chemistry test, you're not really going to be expected to remember and use this equation and actually do calculations, but we're going to discuss it because it helps you kind of understand qualitatively where these reactions go. Okay, so normally we are able to do things at 25 degrees Celsius, so they can combine our gas constant, the temperature, and Faraday's constant. Those are all constants. So when you multiply and divide those, you get this number down here of 0.0592. Okay, this is just a way to simplify that Nernst equation, and as long as we're doing it 25 degrees Celsius, which is pretty normal, we can, that's just room temperature, so it's easy to do. Okay, so like I said, calculations involving this, not going to have to do on the test. However, using this to explain why the energy of a cell would increase or decrease with different concentrations is something you do have to be able to do. So it's totally up to you which way you want to go for it. I'm going to discuss both of them here. But just remember that the cell potential is the driving force because it wants to go toward equilibrium. Okay, just like Q talks about which way it'll shift in equilibrium when we're talking about Le Chatelier's, the Q is going to be the important thing when talking about whether this is the change would increase or decrease the cell potential. Okay, so let's talk about the way this actually goes down. Okay, say we got an electrochemical cell that is a battery. It's thermodynamically favorable. It has a positive E cell. Okay, that means, hey, the reaction happens. It's all the ones that we've seen so far. As the reaction approaches equilibrium, okay, as we get more products, and it gets toward equilibrium until those rates are equal and the cell potential is 0. Okay, remember that at equilibrium, the cell potential is 0. Okay, the reaction will get there. Now, when Q is not 1, okay, it's 1 at equilibrium, okay, when it is not 1, okay, if the ratio of products to reactants is greater than 1, the value of E is going to decrease, okay, because the value, it's going to have to go down in order to get to the K value, okay, so if the ratio is greater than 1, E decreases, okay. If the ratio of products to reactants is less than 1, that means we got more reactants there. Well, that means our reaction is going to go faster. The value of E will increase. We're going to get more electrons flowing. And at equilibrium, the value of E is 0. Okay? So you can kind of think of it on a number line with Q being 0. Okay? Q equals 1 as our standard. Okay? That's when E is our E naught. Okay? Those are equal. And as Q approaches K, E is going to approach 0. Okay? Because K is equilibrium. At equilibrium, no electrons are going to flow overall. Okay, as Q approaches 0, it can't be less than 0 because you can't have concentrations less than 0. E approaches the max. So you want Q to be small. You want to have mostly reactants and not products so that you can get the most electricity. Okay, so let's look at exercise 5. Okay, we have aluminum solid plus 3 manganese 2 plus ions going to 2 Al3 plus ions and 3 manganese solids. Okay, so first we have to figure out E cell, which means we have to go back to our handy-dandy table of standard reduction potentials, and we need to figure out here what's being reduced and what's being oxidized. So let's do that part first. We have aluminum solid going to aluminum 3 plus. So it must have lost electrons or been oxidized. Okay, so our oxidation is aluminum solid going to aluminum 3 plus and 3 electrons. Okay, look it up on your table of standard reduction potentials. Okay, and that value is written as a negative 1.66, okay? Aluminum plus 3 electrons goes to aluminum solid. That has a value of negative 1.66. On our sheet, we've written the reverse of that reaction, so it's going to be 1.66 volts, okay? Now, our reduction here, so I'm changing things weird, is our manganese 2 plus ions going to manganese solid. So we have our Mn2 plus going to Mn solid plus, oopsies, I wrote that wrong. Our Mn2 plus plus 2 electrons going to Mn solid. Okay, and when we look that up on the chart, it is negative 1.88, exactly as it is written. So we have negative 1.18 volts there. Okay. And see, you can kind of see here how we have the 2 and the 3 electrons. That's where, when you balance it out, you get the 2 and the 3 coefficients. Okay, but our standard reduction potential for this cell is 0.48. Okay, so that is our standard reduction potential, and now we have to predict whether E cell is going to be larger or smaller in each of the following cases. Okay, so first, let me go ahead and fill that in. Now, the easiest way, I think, to think about it is to think about it in terms of Le Chatelier's and shifting equilibriums. Okay, so this one, remember, if we were going to write our Q expression here, okay, solids do not get included, so it would just be aluminum 3 plus over the other ion, oh, and this will be to the second power, over Mn2 plus to the third power. So those are our two aqueous ones. Now, Q is going to be 1 at standard conditions. So at standard, okay, the concentration of aluminum 3 plus equals the concentration of Mn2 plus, and both of those are 1.0 molar. That's when the E cell equals 0.48. Okay. And, 1 squared is just 1, so it's just 1. So Q is 1. Now, if we have a concentration of aluminum that is 3 plus, okay, that is in our denominator, and it's also on this side of the equation. So when you increase the concentration of that, it is going to shift the reaction to the left, okay? It's going to cause less products. Q is going to be greater than K, okay, or than 1. So if it shifts it to the left, okay, that means you're going to get less electrons, okay? The reaction's not going to go as fast, okay? So for A, okay, it is a shift left, aka Q is greater than 1, okay? Meaning that our E cell is going to decrease. It's going to be less than E naught, okay? AKA E cell decreases. Okay. Now I'll go back and explain this on the top thing up there, but if you check out the top part of your notes, that number line, you can see when Q is greater than 1, the energy is approaching 0. So E cell is going to be getting smaller. Okay. Now if we look at B, okay, let me change colors here. I'll use red for B. I need more colors here. Okay, B, we have Mn2+, which is 3.0. That is going to shift the reaction in the opposite direction. When you increase 1, it shifts it the other direction. It speeds up the rate of reaction of the forward reaction. So that is a shift right. That means our Q is going to be less than 1, okay, because Mn2+, that's in our denominator. So our E cell is actually going to be greater than our standard reduction potential. It's going to be more than that 0.48, okay, or our E cell increases. However you want to put that. Okay, cool. You could also, of course, plug these into that Nernst equation and use these concentrations and then compare the E cell to the E naught. But for starting out, let's just do this qualitatively because, again, you're not going to have that Nernst equation on your equation sheet. Okay, cool. Okay, cool. Let's look at another one. Where is 3? Is this page 3? Yep. Okay. So another type of non-standard cell is called a concentration cell. It's where they both are the same, but they use different concentrations, okay? If you look at this example right here, both solutions are silver nitrate. You got silver ions and nitrate ions. And nitrates always dissolve, so they dissolve into ions completely, okay? On this side, you have 0.1 molar. On this side, you have 1 molar. So you have 10 times the concentration of it in this compartment on the right. Okay, so it's going to want to fix that, and it's going to want to transfer electrons from left to right to remove some of these silver ions from solution and plate them as silver, solid silver. Okay, so it is another type of cell. So let's look at an example here. Determine the direction of electron flow and designate the anode and cathode for the cell represented here. Okay. So I'm going to zoom on in on it. Okay, so right now we have 0.1 molar Fe2+ on this side and 0.1 molar on the right side. So where does it want to remove ions from to make these equal out? Well, it wants to remove electrons from here. Okay, this one has the higher concentration. So what it's going to want to do is it's going to want to take that Fe2+ and remove those ions from solution, adding it as iron solid, okay, to try to equal out, okay? Things like to be equal. So, therefore, we know, okay, it's gaining electrons, oil rig reduction. Okay, in this cell, we are going to have reduction, which means in this cell, we're going to have oxidation. Okay, now we need to remember, what's going to be going on in this cell. It's just the reverse. Okay, it's going to want to add ions to solution, so it's actually going to be dissolving that solid into iron 2 plus and electrons. So you're going to have the electrons being removed from this one so that they can be gained by this one, okay? That's going to be your flow of electrons from left to right, okay? Now it also asks us to label which one is the anode and the cathode, okay? The easiest way to remember this one is fat cat. Electrons flow from the anode to the cathode. So that means this must be our anode and this must be our cathode. Okay, cool. Okay, cool. Let's go on to another one. This one is a calculation with Nernst. I do highly recommend you try it. However, like I said, you're not going to be required to do it on the AP test. Just to kind of help you guys get set up here, notice these are both standard reduction potentials. This one is more positive, so it'll be reduced. Okay, this one will be our oxidized, the zinc. So we need to flip this reaction. So I'm just going to change it to zinc, 2 plus 2 electrons, and flip the sign. So our standard reduction potential for this reaction is 1.76 volts. Okay, and it is at 25 degrees Celsius, so we can use that Nernst equation where E cell equals E naught minus 0.0592 over N log of Q. And Q, in this case, we have to write to that overall reaction. Okay, so we're going to have to add up these. We're going to have to multiply this top one by 2. So we got a 2 there, 4 there, 2 there, 2 there, 2 there. Okay, so the electrons can cancel out. We have 2VO2 plus our zinc solid plus 4H plus going to our 2VO2 plus zinc 2 plus H2O. Okay, so remember in our Q expression, our solids like the zinc and then our pure liquids like water don't get included. So the Q expression would be products, so concentration of VO2 plus squared times the concentration of zinc 2 plus over our concentration of VO2 plus squared and H plus to the 4th. Okay, so if you plug in these values into here, you should get an E cell of 1.89. I'm not going to take up your time with that, but it's definitely something you can try just to prove what's going on. But notice the VO2 plus is the one that's getting quite a bit bigger. The VO2 plus is getting smaller. Okay, so that means that this is getting smaller, this is getting bigger. Our Q is going to be less than 1, which means we expect our E cell to increase, and that's what you should see. Okay, cool. Okay, cool. Now, last but not least, we're going to do one example problem with, the Gibbs free energy end cells. So using these two equations, the fact that delta G for an electrochemical cell is our minus nuff, and then we can relate it to equilibrium through that Ratlink equation that we've done before. Remember, these are our favored conditions. These are how things like to be spontaneous. Okay, let's look at the example problem. For the oxidation reduction reaction, blah, 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 blah. Here are the half reactions. Balance the redox reaction, calculate E naught and K at 25 degrees Celsius. Okie dokie, here we go. They gave us the reaction. Which one of these standard, notice they're both written as reductions. Which one of them is more positive? That's going to be this one. So this is going to be our reduction potential. So we're going to have to flip this one. Again, I'm just going to flip it by canceling this out, knowing that this is now 2 plus, and this is 3 plus, and then there was an electron there. Okay, and flipping the sign on that one. So it gives us our standard reduction potential of 0.67 volts. Okay, now we have to add up the reactions, okay, in order to balance it. So we got 2 electrons here, so we're going to have to multiply this one by 2 in order to add them up. I'm going to add them up just below it so that it's easier to see. Okay, so we have our S4062 minus plus R2 CR2 plus going to 2 S2O3 2 minus plus 2 CR3 plus. And note the number of electrons involved in this, our N, is going to be 2 because there are 2 electrons involved in the balanced reaction. Okay, so now we have our E naught, that's the 0.67. We need to find K. So we're going to put, find our delta G and then set those delta G's equal to each other using the Nernst equation and the Ratlink. So remember how the equations went. It is NF E naught equals delta G, but then delta G also equals RT ln of K. Okay, oopsie, I forgot my negative signs there. So we can simplify this by erasing that delta G, and it's negative equals a negative, so let's just go ahead and erase those negative signs too. Okay, so now these, no, hold on, it won't give up on me. Okay, so now those two things are equal to each other, and we can just start plugging things in. So 2, again, you look up Faraday's constant from your equation sheet, and it is 9.65 times 10 to the 4th times our E cell, which is 0.67, equals R. We're going to use our energy R, which is 8.31. Our temperature in Kelvin, so that's 298. And natural log of K, which K is what we are solving for. Okay, so you plug this all into your calculator, and you get 52.2 there. And let's see, 8.3. Oopsie, nope, that's not right. Sorry, I skipped a step. 2 times 9.65 times 10 to the 4th times 0.67. That gives me 129,310 equals 8.31 times 298, 2,476.38 times natural log of K. Okay, divide both sides, so 129,310 divided by that number that we just got, and you get 52.217 equals natural log of K. To undo the natural log, you do E to both sides, and that cancels that out. So E to the answer gives me a K value of 4.76 times 10 to the 22 equals K. Okay, cool. Okay, cool. Go ahead. Oh, just so you guys know what these kinds of things are used for, all batteries, okay, whether they're the batteries in your car or the batteries that are in your phone or whatever you use batteries for, okay, they're all there. There's also fuel cells that they use in spacecraft where the battery has to last a really long time and supply a lot of power, where they actually have the tanks where they're continuously pumping in new materials for these cells. Okay, so yeah, go ahead and do the self-check, and that's it for right now. Okay, cool. Okay, cool.